Hello everybody, let's go ahead and just recap some ideas that we've covered so far from chapter 5. We do have this theorem. This is our limit definition of an integral. Okay, so it just says if f is integrable on the interval from a to b. Okay, so integrable means you can take the integral of it. Then it's saying the definite integral from a to b of f of x dx is equal to the limit as, oops, I see a typo. This should not be x, this should be n. As n approaches infinity, okay, and you sum up all the areas of those triangles. So you're taking the sum from I equals 1 to n of x, f of x sub I times delta x. Okay, so what this is telling me right now is that I can find my exact area by setting up all these Riemann sums. Okay, this is our Riemann sum part. And if I go ahead and calculate all the area of these rectangles and I make n approach infinity, okay, well, n is your number of rectangles or your subintervals. So if I take my number of rectangles and make there be infinitely many rectangles, it will give me the exact area, which means it is the integral from a to b, okay? The other thing that you guys should maybe take note of is just some notation. This is our sum notation. Okay, sigma notation, it's telling me to sum up all of those areas where we added them together. If you notice, your integral kind of has a fancy stretched out S shape. Okay, so it's showing that sum as well. Okay, and then it's just telling me what delta x is. That's your b minus a divided by n, your number of subintervals, and then your x sub I is a plus I times delta x. Okay, and you guys kind of work through that as you worked with your limit definition in section 5.1. Okay. Once again, here is our integral, okay? Some parts of it, just kind of to make sure we're understanding what's all going on. This right here, this is our integral sign. And like I just said, it should kind of symbol an S, okay? Because it's saying sum all of those areas up together. And then what we say is we're going from A to B. This is what we call our lower limit. It's a smaller number. And then b would be considered our upper limit. Okay. Then f of x is the function that we are using. Okay. And so this is our function that we are looking at, or the curve. And it's also called the integrand. Okay, that's what you're taking the integral of. And then the dx. It's important. The dx is telling you the variable of integration. Okay, so who are you taking the antiderivative with respect to? Okay, and just remember that integrals find area underneath a curve. Okay, and then here's just a few examples. Okay, the one on the left, it's got midpoints. Just reminds you that this is the good old Riemann sum, and this provides us with an estimate. Because as you can see, we're missing some area here and we have a little bit of overlay here, okay? But when you actually have the integral from a to b of f of x dx, it's nice and smooth, you're finding every part of it, and so this is our exact area. And the equivalent to this, once again, is that limit definition, okay? And then here's just one last example, okay? Once again, on the left, this is our Riemann sum example, and the one on the right is our definite integral exact answer. Okay, so just kind of to clear that up. And then just some things to take note of your homework. Number 26b, draw pictures with rectangles. Okay, that's what I want you to do. And then set 26d, just label positive and negative areas. That's what you need to do for those two. Okay, and then 26, make sure you see that you do not have to do part C. All right, so that does it for section 5.2 day 1. I will see you guys next time.